Swayam Prabha. Digital India. Educated India.
This basically this is very simple. How to transform a vector from one coordinate system to another coordinate system. This is basically CS and minus SC. So U dash V dash is CS minus SC. So this is how we normally write. Now, how do I change the strain from one coordinate system to another coordinate system? Because previously, you remember I told you, since it's a tensor quantity, you cannot use this dot product cost product for tensor quantity. So what happens is now you have to go to the basics of the definition. So right now I told you epsilon x dash will be del u dash by del x dash, because this is in that direction. U dash and x dash in the same direction. And then if you use the chain rule, we will do this because x dash is now is function of x and y. So we can use that chain rule here. So if we use that chain rule, now del u dash by del x, this one, we will be using C del u del x plus S del v del x. And similarly, this one you already know. I just told you this is C and this is S. And this is coming from where? In the first equation. Here, from here. This is C, this is S. So del u del x C and del v del x S. So this is written like that. Then if we just multiply here, you will see this comes like this. Okay. So epsilon x dash is C square epsilon xx. Epsilon xx. S square epsilon yy plus CS gamma xy. Okay, you see, this is just simply not converting from one direction to another direction. Okay, because it is not a vector quantity. Remember that it's a tensor. So now for other direction strain tensors, like this is epsilon yy and this is gamma xy, do not consider this at this point of time. So this is my three-directional strain tensor. So for converting from one coordinate system to another coordinate system. Okay. So what do we have? C square A square CS, A square C square minus CS, and this is this. This is for gamma xy. Okay. The entire derivation you will find in the book. I'm not getting into the derivation that much. Now, what is the usefulness of this? Now, for that, let me show you a exercise problem which you will do. I'm just giving you the problem. You are able to see this? Exercise 1 written on the top.
Yes, sir. Yes, sir.
Right. Now, what it says is the first problem. A 45-degree strain rosette is pasted on a side of a railway track. You know railway track, on its side, we have pasted a 45-degree this thing. When some rail is passing through, we are going to measure the strain in three directions. One is in X direction, one is in Y direction. Let's say Y vertical, X is along the track, and this is B is at 45-degree from the axis of the track. And angle between A to B and B to C both are 45 degrees. Now, at a certain point of time, we found the strain. This is to the power, okay, -6. A strain at strain gauge A is 540 into 10 to the power -6. In B is 210 into 10 to the power minus 6, and C is minus 60 into 10 to the power minus 6. What you have to tell me that what is the value of gamma xy? Can you solve this problem? I can give you a hint, but I want you to calculate. The hint is this OB direction, you consider the x dash direction. Okay. I give you about 2-3 minutes. You do it. You have a pen and paper and calculator with you, right?
Yes, sir.
Okay. The hint is OB direction is my x dash direction. Okay. This is the hint I'm going to give you. Please do that. Everybody understood the problem? You have to estimate gamma xy. And OB direction is x dash direction. If you have not written the formula, I'm showing you again. This is the formula.
Sir, question please.
Question is to find out gamma xy.
And can you share the question once again?
Okay, wait a minute. Question is to calculate shear strain gamma xy here. Anybody? This is a very simple calculation. I have already gave you hint, everything. See, this is the epsilon 45 degree. So what will be C square? The C square will be
1 by 2.
half. Okay, 1 by root 2 whole square. Plus 45.
Sir,
Yeah.
is it minus 60 into 10 to the power minus 6?
Maybe I did not calculate. But see, this value is given to you. If this value is given, this value is given, only this is not there. All others are given because you are calculating at 45 degree angle. So this is given to you 210. This is epsilon xs given 540. And this is given minus 60. Okay. So you have to just put it there and you will calculate this value. So I can tell you, you can write it half into 540 plus again half into epsilon yy, which is minus 60, and CS is also half. So 45 degrees is very easy. Gamma xy you do not know, and this is given, I think, 210. So whatever the value comes, that is your the shear strain. So you are seeing the importance of this formula. Normally, we cannot directly measure shear strain. We can measure only one directional strain. But if we use three strain gauges in one go, we'll be able to also measure the shear strain. And this formula will be used. Okay. Then we go further. Oops. Something is happening. Where is the cursor? Yeah, I got the cursor. Now we go to transformation of stresses. Now this figure a little bit clumsy though, but let's assume this is a rectangular, triangular element, and the sigma xx tau xy and sigma yy tau xy is being applied. This angle is theta, and this is that x dash direction which is perpendicular to this line. So this one will be theta degree, and y dash will be parallel to this. Basically, I have done this dotted to just show you how that element is oriented. Basically, you may think, where is my sigma y dash y dash? Okay, it is there. Okay, it is in this plane. In this plane, we only have tau x dash y dash and sigma x dash x dash. Okay. Now, there are many ways we can transform many different methods. So one of the simple method here is to balance the force. Okay, applied in this triangular element. So if I assume this area is A, so these become A sine theta and this one will be A cos theta. If this area, meaning the, let's say the length A, then it is A sine theta, A cos theta. And when we get this, we can write two equations. One is in x directional force. So you can see sigma xx into A cos theta, that is the area, plus this tau xy into A sine theta. Then we have converted this into X direction and Y direction. And so this is given you like that. So we can write one equation like this, assuming there is no force due to its density, means due to its own weight. And the second equation, all the forces in Y direction, we can write it like this way. And here there is two unknown, this one, sorry, three unknown, this and sigma, sorry, here it is two unknown, sigma x dash and tau x dash y dash. And we can very easily solve this. And when we solve, we'll get something like this equation. Okay, these are the three equations we will directly get. The middle one we'll get by making this another plane. From the above two equation, we'll get this one and that one. And if you consider the other plane, then we'll get this one and this one. Same thing. So these are the trace transformation for stresses. And if I have to again write it into a matrix form, that how these three tensors, the transformed tensors is related to my original stress tensors. It is related by this T. Now here also you can see C square and how it is coming to C square. You can see this sigma xx. Here is also sigma xx. So if you combine this is 1 plus cos 2 theta. And you know the formula. This is 2 cos square theta. And 2 cos square theta divided by 2 will be cos square theta. So this is in short form. It is written here using that matrix. Right now you will not consider this column and this row. Only these three is fine. So this T is the relationship between stress transformation. As I told you in the book, I am not done this way. In the book, it is done in another way, but the same result will come. Okay. So this is how we do stress transformation from one coordinate system to another coordinate system. Again, do not do that mistake. I have seen repeatedly when a problem is given in the exam, what student does the mistake, they consider it is a vector and they just do the cos theta and sin theta. Okay. Always remember that this is a tensor. You cannot directly apply the vector related operation in a tensor quantity. It will be completely wrong. Okay. Because the area is also getting changed. So you cannot apply vector operations in a tensor quantity. Okay, now we will do another exercise. You read this, it's a very simple, and I'll flash you the equation again, but you do it. The vertical and horizontal stresses at the middle of a coal pillar are found to be 15 MPa and 3 MPa. So in the element it is shown. Can anybody tell me the shear stress direction it is shown? Is it positive or negative direction?
Negative.
Positive.
You have to tell me whether you are speaking for rock mechanics or solid mechanics. For rock
Positive
mechanics,
for rock mechanics.
rock mechanics what?
Positive.
Yes. So it is a positive configuration for rock mechanics. So when you use in the formula, okay, what value you will use, positive or negative? If the formula doesn't know, you are solid mechanics or rock mechanics. As a formula, let me show you again. This is the formula. So here you will use the positive value. Okay. This formula is also made for rock mechanics. So you can use it. You will have to use the positive value. So now, if you have not copied the values, you just copy it and do. So 15 MPa in sigma YY, you can write it down in your paper. 15 MPa is sigma YY. 3 MPa is sigma XX. Both are positive because we are showing the compressional. Shear stress, the configuration which is given is positive, is 2.5, and theta, angle theta, tell me it is positive or negative?
Negative.
Yeah, negative because it is rotating clockwise. Okay, so now I go back to the equation. Probably you have not written the equation. Have you written the equation? So I go back to the equation and you can now tell me these three new stress tensors. And I will give you, this is a problem from the book. So I'll be able to give you the answer. You just quickly multiply. You quickly multiply. C square will be cos square 30 degree minus 30 degree. A square will be sine square minus 30 degree and all this. So how much you got? The first one, sigma x dash x dash.
So 3.835.
Positive or negative?
Positive.
Okay. You keep that value. We'll use it in another example also. Sigma y dash y dash
17.165.
14.165. Okay. And tau x dash y dash
Minus 1.34.
minus 1 point. How much? Minus 3.946. Everybody got that? Minus 3.946. Okay. All right. So this is just a multiplication of matrix and vector. That's it. Okay. Nothing to be worried about. But now the question comes, what is principal stresses? Now, if I go to the principal stress, by definition it says the principal stresses are the normal stresses that act in planes where shear stress does not exist. Okay, so that means now I show you the exercise what you have done. I see this, I told you positive, right? 2.5. You have used 2.5 as a positive value. Now, while you have rotated this 30 degree, what happened to shear stress in this direction? It become negative value, isn't it? So it changes from positive to negative. So when it is changed from positive to negative, that means it definitely crossed zero. So that zero, where the shear stress becomes zero, there will be a plane in between this 30 degrees, 0 and 30 degree. There is a plane where the shear stress is zero. And that particular plane is called the principal plane. And the normal stress act on that plane is called the principal stresses. So that means there are some plane where the shear stress will be zero. Now, how do I directly calculate it? I know the shear stress formula. I can directly put it zero. And if I directly put it zero, then I find the theta p, p meaning the principal plane. So I can actually, I can actually calculate this, I can actually calculate this, the angle from the x-axis. So it is basically tan 2 theta will be 2 tau xy sigma xx minus sigma y. Okay. Now, in this way, I am able to calculate the angle, but there is a question here, because there are two principal stress, right? We have two plane. One is in x dash direction, another is in y dash direction. So in the two plane, this angle belongs to which one? This is not clear from this. Angle calculation is correct. So that's why we do little bit alternate way. We assume, let's say, that this is sigma I, which is my principal stress. And there will be no shear stress. So I'm looking for a theta where there is no shear stress, only normal stress act. So if I now balance the equation, the force equation in two direction, so I can write C sigma xx plus S tau xy, like I have written before, is minus this, and this is also minus this. So if I put it into a vector form, this, if I write in a vector form, it becomes like this. So sigma xx minus sigma I, then tau xy, sigma yi minus sigma I, C and S is equals to 0. Have you seen equation like this before in your math 1 or math 2?
Yes, sir.
Where did you use this? To calculate the eigenvalue. You remember that? The equation become Ax equals to 0. I think they have told you about the system of linear equations where Ax equals to B. Now, if B becomes 0, then what happened to the system of equation? Okay, because this may be very trivial solution. One is 0, 0. This will give you the solution that. But other than 0, 0, is there any solution? How did you solve? You have put a lambda, you remember, in the diagonal position, and lambda was told to be your eigenvalues, and the vector x then become the eigenvectors. Now there you have done math. Probably you didn't understand that time where is the application. Now I'm showing you a simple application in principal stress. Basically, the principal stresses are nothing but the eigenvalue, and the eigenvector is its direction. Okay. Now I'm not going to tell you the importance of eigen, why you have to learn all this. So to solve this one, what you did, if you remember in math 1 or math 2, I don't know which math they teach you this, is the determinant of this matrix must be 0. So if I apply that, the determinant of this matrix is 0, I get something like this, where N1 is sigma xx plus sigma yy, and N2 is minus sigma xx sigma yy plus tau xy square. Now, this equation, or this N1 and N2, are called the stress invariants. It's a very important part of stress analysis. It's called stress invariants. I will come to that when I will come to the Mohr circle. The stress invariants are, these two variable will not change its value even if you change the coordinate system. That means this equals to sigma x dash plus sigma y dash. Okay, this equals to the same, and here you can just replace by any x dash y dash. Okay, the value of n1 n2 will remain the same, it will not change. At a particular location, if I know the 3 stress tensor, even if I change the the coordinate system, another coordinate system, the stress invariance values will not change. Okay. Now, can you verify with the example problem you have done? Just have you done just before you have done that, right? Can you check these two are correct or not? At least the first one, first equation N1. What was the sigma xx plus sigma yy in that example problem?
18, sir.
18. And when you got the two other values, what is the sum?
Sir, it's also 18.
So that time you didn't recognize that, but you take any theta, you take 60 degree, you take 120 degree, you will see that two plus remains the same, will not change. Okay, same for N2 also. And if we do the 3D, there will be another equation, and these two equations will also change. This is given in the book, you can look. In this class, I'm not going to tell you about 3D because it will be too much. But as far as 2D, these two are remain the same. And then if I actually solve this, because still I didn't find out the sigma I. So if I solve this, this is a quadratic equation and it can be easily solved. So the quadratic equation becomes like this. Now you see, I have put the subscript sigma 1 and sigma 3, and they are given respectively plus and minus. So there are two basically. One is sigma 1 with plus, and another is sigma 3 with minus. Okay. So the values of principal stresses or your eigenvalues are these. Now can anybody tell me then how do I find the eigenvector? The direction? Okay, let me do what? Why don't you solve that problem? You have found that, right? Let us calculate the principal stresses of the exercise I have given you.
It's 2.5 or 15.5.
2.5 and 15.5. Perfect. Fantastic. So you have already find out this thing. Now, what is the direction? What will be the angle theta? How do you find that out? That means the vector C and S. How do I find the vector C and S? This. Value you got, eigenvalue you got. I have no issue with that. Now, how do I find C and S?
We can replace it in the equation of tangent 2 theta is equal to 2 sigma.
No. You use this equation. Okay, you put 15.5 here. Okay, so this is 3 minus 15.5. Why don't you write 3 minus 15.5? This is 2.5. This is 2.5. And this is 15 minus 15.5. Okay. And you multiply the first row. So this happens minus 12.5 C plus 2.5 S is 0. So there is a relationship between C and S. What is that relation from the first row?
So it's minus 12.5 C plus 2.5 S is equal to 0.
Okay. So the relationship between C and S will be C equals to something you can write. Okay. And if you use the second row, what happened to if you write it for the second row?
The same, C equals to 5.
5C minus 0.5 S is equal to 0.
So it is the same equation.
Yes.
Right? It has to be same. That's why you are using eigenvalue. Okay. Because this doesn't have a unique solution. Now, how do I then find out what is C and S? Can anyone tell me?
C square plus S square is equals to 1.
Perfect. So we have another relationship called C square plus S square equals to 1. You now put that, then you find the C. C is nothing but cos theta, and you know the theta. Now you will also get value of theta, two values. And since you have used here 15.5, so this is the angle with the major one. That means the maximum principal stress. Whatever that theta comes, this is with the major principal stress. The maximum value we call the major principal stress, and the minimum value we call the minor principal stress. Okay. So if you put here 15.5, whatever the angle you will get, this will be with the major one with x-axis. And if you put 2.5 instead of sigma I, then whatever the angle you will get, it is with the minor one. But they are anyway 90 degrees apart, so you do not have to worry. Now you will see two values of theta. Why two values of theta? Because you will see another one is right in the 180-degree apart, because we have two surfaces, right? One in the right side, one in the left side where sigma x-axis is acting. So it can be in the either direction. That's why it will give you the two value. So that's why normally to calculate the principal stresses, we go by this method. This is a very prudent and right method of calculation of the principal stresses, both major and minor, as well as its direction. Okay. I hope it's clear to you how to calculate the principal stresses. There should not be any confusion. When we'll do more circle, you will know much better. Now we come to the maximum shear stress. Is there any plane where shear stress become maximum? Oh yes, there will be a plane, okay, where shear stress will be maximum. Now how do you find that out? You take the derivative of shear stress with respect to theta and you make it 0. This is the first condition. And then you will find the angle and use that angle to calculate the maximum shear stress. Okay. So you will know the angle from this equation, and then you put that into this original equation in place of theta, and you will get the maximum shear stress. So there is a plane where shear stress is maximum. So there is a plane where shear stress is 0, and there is a plane where shear stress is maximum. Okay. Now, why we are interested in this? Sometime, not sometime, majority time, if a rock has to fail or any material has to fail, it basically fail along the maximum shear stress or along the minimum principal stress, or perpendicular to minimum principal stress. So normally a crack happens in two ways, one along the maximum shear stress or along the minimum principal stress, or along the minimum principal stress. Okay. Not along, sorry, perpendicular. I'm sorry. The perpendicular to minimum principal stress. Okay. We'll come to that when we tell you about the failure of rock and all these things after a long time, not now. Okay. So these are very important. So what I'm telling you today is basically the definitions of these stresses, how we calculate it, and what is its applications in the actual field. Because nothing goes waste here. Okay, everything we will use. Okay. So if you want, I can stop for 5 minutes. If you are a little bit tired, then we can start again at 11, if you like. There is one more topic left, more circle, and that requires your maximum concentration. So I can stop the recording and stop sharing also, and then we will go to the more circle. Okay, is that fine?
So we have another class at 11.
Sir, we have class at
Oh,
11.
is it? Oh, you have a class at 11. Oh, I see. Then let me finish that. Oh. Now, you see, these are the three equations. The stress transformation equation has been given. Do you see, especially between using this one and this one, forget about the middle one, this one and this one, do you see the equation of a circle? Anybody? you probably do not see. But let me tell you one person called Otto Moore. He has seen that thing probably 150 years ago. Okay, he said, this is a equation of a circle actually. Okay, and how he has done, this is given in the book. See what he has done. He has taken this minus that, he has done square it, and he added this, squared it, and he added it, and he found that. And this is nothing but, you can see, I can put as a r square. These are all constant because sigma xx, sigma yy, theta, everything will be given to me. So this become a constant r square. So you can see x minus c, or x minus, let's say some coordinate of center, and y minus 0 square, so is equals to r square. So the center is this 0, sigma xx plus sigma y by 2, 0 is the center, coordinate of the center, and this is basically r square. This is basically radius, and that can also be reduced very much. So basically, this is a equation of a circle with a angle 2 theta. Okay, but you remember that actually we are rotating theta. Actually, we are rotating the element theta, but the circle we are making with 2 theta. So physically we are rotating theta degree, but in the Moore circle it is rotating 2 theta degree. So whatever angle we measure in a Moore circle, this will be by half to get it into the actual rotation. Now I show you this. This is a plane, sigma xx this. Let's say this is a dash plane, and a plane is this vertical, horizon, vertical plane is, this plane is basically the a plane, the vertical plane is the a plane. Now here I have mentioned a and a dash, that's why. Now how do you plot a Moore circle? First of all, you have to take a graph paper. See, this is also called the graphical representation of stresses. So whatever the 3 equation I gave you before, the representation of that in graphical form is what is Moore circle. To draw a Moore circle, you do not need any calculator. Remember that. He has drawn it 150 years ago. There was no calculator at that time. So that time also he didn't need it. This time also we do not need it. But I have seen the students immediately start using calculator to draw a Moore circle, but actually you do not need. Now I tell you how. Now you see there is 2 plane. The vertical plane we have shear stress sigma xx tau xy. In horizontal plane we have 1 point which is sigma yy tau xy. Okay. Now we have to plot it in a graph paper. So in a graph paper you draw 2 perpendicular lines, sigma n, which is basically the normal stress, and tau is in the vertical. Now you see I have given the rotational thing. This is plus, this is minus. So if a plane is rotating clockwise, you will consider it to be minus. And if a plane is rotating counterclockwise, you will consider it to be plus. Okay. Now with this concept, I take the plane A, and here we have sigma xx and tau xy. So this vertical plane you are seeing, it is rotating clockwise. So the tau xy value you will take as a negative. So this becomes sigma xx and negative tau xy. You can see, because it is clockwise rotation, so tau is negative. Now in A dash plane, This is sigma yy is my sigma n, and this plane is rotating counterclockwise. So this tau xy will be positive. So you have to plot these 2 points here. And when you are doing sigma n and tau, always remember that both the axes, the gradation should be same. Gradation should be same. In other word, if this is let's say 1 MPa from here to here, this thing will be 1 MPa from here to here. Otherwise, it will become like an ellipse. Okay, it will not become like a circle. So your gradation should be same in graph paper. Then we plot these 2 points and draw a line. Okay, so a dash line is drawn. Wherever it cuts the horizontal axis, that is basically the center of the circle. So far clear? I do not need calculator. Now you take your compass, and this being the center and this being the radius, this is OA dash or OA is radius, you draw the circle. So that completes your mode circle of stress. You do not need calculator yet. Now, this circle cuts the horizontal axis into two places. This one is my sigma 3, minor principal stress, because shear stress is 0. You see, here shear stress is 0. Here is also shear stress 0. So this is my sigma 1 because this is the maximum value. Okay. So this become my sigma 3. This become my sigma 1. Now this is the angle 2 theta for principal stress. Okay, this is the angle 2 theta for principal stress, because this A dash plane is my x-axis direction. So x-axis direction to clockwise direction if you come. So you will get what you measure with a protractor, you measure the angle. Whatever the angle you get, divided by 2. Do not forget divided by 2, because this circle is made with 2 theta angle, not theta angle. So actually you have rotated theta degree, but in the circle it has rotated 2 theta degree. So that means this theta 1 is my angle from x-axis towards the major principal stress direction. If you measure into this direction, that will become the minor principal stress direction. So from more circle of stress, I can find any. Then let's say if we say, okay, if I rotate counterclockwise 60 degree. So if this one is rotated counterclockwise 60 degree, what happened to my stresses? What is the new stresses I get? So counterclockwise this, so this A dash point will go to E. Then from here you draw a perpendicular to here. So from here to here it will become your normal stress, and here to here it will become your shear stress. Now from the shear stress, positive or negative, you will know which direction to put here, which direction to give. If it is negative, you give negative. If positive, you give positive. Okay. So this is what how you construct the circle of stress. I will request you to draw more circle of the exercise problem what I gave you. Okay. And when they come for tutorial, you show it to them that, or you can send it to them also, that you are able to draw a more circle. This is very, very important. Then the last thing what I want to show you.
Excuse me, sir.
Okay, your class will start,
Yes,
right?
sir, we have a class.
Yeah, then I'll stop here. Maybe next class, we will little bit touch upon this, and then we'll finish this chapter 4 in the next class. Okay. So thank you very much, and we will see again on Thursday, 3 to 4. Okay.